The sun rises, a new day begins. It's a sight we often take for granted, this brilliant star gracing our sky. But the sun is more than just a source of light and warmth. It's a cosmic powerhouse, the anchor of our solar system, and the giver of life itself. The sun dominates our sky, a giant ball of burning gas. It's a force to be reckoned with, capable of both nurturing and unleashing its power on a colossal scale. Without the sun, our planet would be a barren, frozen wasteland. There would be no life, no oceans, no swirling atmosphere. The sun's story is one of immense power, incredible scale, and a life cycle that spans billions of years. It's a story that intertwines with our own existence in the most fundamental ways. To understand the sun is to understand our place in the universe. Let's embark on a journey to our nearest star to unravel the mysteries of this cosmic powerhouse that holds dominion over our solar system. Our sun wasn't always the majestic star we see today. It began its life billions of years ago as a cloud of gas and dust, a nebula drifting through the vastness of space. This nebula, like countless others scattered across the universe, was the birthplace of stars. Within this swirling cloud, gravity was at work, pulling particles together. Slowly but surely, the nebula contracted, its core growing denser and hotter. As more and more material clumped together, the temperature and pressure at the center continued to rise. After millions of years, the core of this collapsing nebula reached a critical temperature. It was then, under the immense pressure and heat, that nuclear fusion ignited. Hydrogen atoms fused together, forming helium and releasing an incredible amount of energy. And with that burst of energy, a star was born. Our sun, a giant ball of burning plasma, came into existence, illuminating the darkness and forever changing the cosmic landscape. Deep within the sun's core, the furnace of our star burns bright. It's here, in this unimaginable heat and pressure, that nuclear fusion takes place, powering the sun and bathing our solar system in light and warmth. The core is a place of intense energy, with temperatures reaching 27 million degrees Fahrenheit. It's a dense and chaotic environment where hydrogen atoms are constantly colliding and fusing to form helium. This process releases a tremendous amount of energy in the form of light and heat. The energy generated in the core is what sustains the sun. It's the driving force behind the sun's incredible luminosity and the source of its gravitational pull, holding our entire solar system in its embrace. But the journey of this energy from the sun's core to its surface is a long and arduous one. It must traverse through several layers, each with its own unique properties and challenges. Surrounding the sun's core is the radiative zone, where energy travels slowly in the form of photons. These photons bounce around, absorbed and re-emitted by atoms countless times. It can take hundreds of thousands of years for a single photon to escape. Next is the convection zone, where energy is transported through plasma movement. Hot plasma rises, carrying energy towards the surface, while cooler plasma sinks back down. This creates a pattern of convection cells, resulting in the sun's granulated appearance. Finally, we reach the photosphere, the visible surface of the sun. This is the layer we see from Earth, a blindingly bright sphere of plasma. The photosphere releases the sun's energy into space as light and heat. Section 5. The sun's energy, light and life. The sun's energy, radiating outwards into space, is the lifeblood of our solar system. It's this energy that sustains life on Earth, driving our weather patterns and influencing the climates of planets. Here on Earth, we receive only a tiny fraction of the sun's total energy output. Yet this small fraction is enough to power all life on our planet. Plants use sunlight to convert carbon dioxide and water into glucose, releasing oxygen as a byproduct, a process known as photosynthesis. This process forms the foundation of most food chains on Earth, providing energy for plants and, in turn, for the animals that consume them. The sun's energy is what allows life to flourish on our planet. But the sun's influence extends far beyond our planet. Its gravitational pull holds all the planets in our solar system in their orbits, dictating their paths through space. Without the sun's gravity, our solar system would disintegrate, the planets flung outwards into the vastness of space, The sun's energy and gravity are the invisible forces that bind our solar system together. Section 6. Earth's seasons, a solar dance. As Earth orbits the sun, our planet's tilt creates a cycle of seasons. The Earth's axis is tilted at an angle of 23.5 degrees, and this tilt remains constant as we journey around the sun. During summer in the northern hemisphere, the North Pole is tilted towards the sun, receiving more direct sunlight. The days are longer, the sun climbs higher in the sky, and temperatures rise. Conversely, during winter in the northern hemisphere, the North Pole is tilted away from the sun. The days are shorter, the sun hangs lower in the sky, and temperatures drop. The southern hemisphere experiences the opposite seasons. When it's summer in the north, it's winter in the south, and vice versa. This cycle of seasons is driven by Earth's tilt and its orbital dance around the sun. The sun's energy, distributed unevenly across our planet due to its tilt, creates the variations in temperature and daylight hours that define our seasons. It's a reminder that even from millions of miles away, the sun's influence on Earth is profound. Section 7. Solar storms. The sun's fury. The sun, while a source of life-giving energy, can also unleash its power in dramatic and sometimes disruptive ways. Solar storms, eruptions of energy and charged particles from the sun, are a reminder of our star's volatile nature. Solar flares, sudden bursts of intense energy, are among the most powerful events in our solar system. These eruptions release energy equivalent to millions of hydrogen bombs, sending bursts of X-rays and ultraviolet radiation hurtling through space. Coronal mass ejections, or CMEs, are another type of solar storm, releasing massive clouds of plasma and magnetic fields into space. These eruptions can travel at speeds of millions of miles per hour, carrying billions of tons of solar material. When directed towards Earth, solar storms can have a significant impact. Solar flares can disrupt radio communications, interfere with GPS signals, and even pose risks to astronauts and satellites in orbit. CMEs, upon interacting with Earth's magnetic field, can trigger geomagnetic storms, disrupting power grids, causing widespread blackouts, and creating stunning auroras. Section 8. Auroras, dancing lights of the sky. While solar storms can have disruptive effects, they also create one of the most breathtaking spectacles in our night sky: auroras. These shimmering curtains of light, known as aurora borealis in the northern hemisphere and aurora australis in the southern hemisphere, are a testament to the sun's power and beauty. Auroras occur when charged particles from the sun, carried by solar wind or CMEs, collide with atoms in Earth's atmosphere. These collisions excite the atoms, causing them to release energy in the form of light. The colors of the auroras depend on the type of atom being excited. Oxygen produces green and red light, while nitrogen emits blue and purple hues. The result is a mesmerizing display of dancing lights, painting the night sky with vibrant colors. Auroras are most commonly seen at high latitudes, near Earth's magnetic poles, where the planet's magnetic field lines converge. They are a reminder of the interconnectedness of our solar system, where even the sun's most powerful outbursts can create displays of ethereal beauty. Section 9. The sun's destiny, red giant to white dwarf. The sun, like all stars, has a finite lifespan. It's currently classified as a main sequence star, fusing hydrogen into helium in its core. In about 5 billion years, the sun will run out of hydrogen fuel, the core will contract and the outer layers will expand, transforming it into a red giant. The sun will swell, possibly engulfing Earth. It will shed its outer layers, forming a planetary nebula. The core will become a white dwarf, a dense remnant. Section 10. A star's legacy. The sun's story is one of immense power, incredible scale, and a life cycle that spans billions of years. It's a story that began with a collapsing cloud of gas and dust and will end with a fading ember, a testament to the impermanence of even the most massive objects in the universe. But the sun's legacy will live on. The elements forged in its core, scattered into space during its red giant phase, will seed the formation of new stars and planetary systems. The sun's energy, captured and stored by life on Earth, will continue to power ecosystems long after our star has faded away. And the light from distant stars, some perhaps born from the ashes of our own sun, will continue to illuminate the night sky for billions of years to come. As we gaze upon the sun, let us remember that we are witnessing a cosmic powerhouse in action, a star that has shaped our solar system and made life on Earth possible. It's a reminder of our place in the grand scheme of the cosmos, a small planet orbiting an average star yet forever connected to the universe's grand cosmic dance.